Nice and loud. Cool. All right. So for those of you that are attending via Zoom, it might be difficult for me to like see the chat because I'm gonna like hide everything. So either unmute yourself and just like interrupt me, or I'll have a couple pausing points where I check the chat. But please feel free to interrupt me. Do not hesitate. I'll be happy to answer any questions. Okay. Hi everybody. It's Berkeley time, so let's go ahead and get started. If you haven't already, scan the QR code for attendance link. It's important that you do that, and I'll let everybody do this for like maybe 30 seconds before we move on to the next slide, because there's also going to be another QR code with a couple bit of announcements. Just so everybody's clear, homework 4 was due just now. I hope it wasn't too challenging. But if it was, that's okay. We had a lot of people come to office hours. Like I think there was like 8 or maybe even 10 on Monday, and it seemed like there was quite a few of you today at Raphael's office hours. So glad to hear that y'all are getting the help that you need. If you're still struggling though, please come to more office hours. We have one every single day, and we also have a Discord. I'm trying to keep up with answering questions, but yeah. So I'm gonna go ahead and move on to the next slide. So we got some announcements for today. Office hours are important, like I was just saying. The attendance link is written right here. If you want to type it in, and if you don't have access to like a camera at the moment, you can type it in. And then homework 4 was due just now. And then homework 5 will also be released today. That'll cover some curve fitting, some root finding, and numerical integration and differentiation, which we're going to talk about today. And then really quickly fill out another survey. So this QR code over here, that is going to allow us to gauge final project interests. I know we're only halfway through the semester, but we want to make sure that your final project is kind of like a big shebang and something that's really cool to showcase. So we put a lot of effort and like emphasis on your final projects. So we're already starting this week to gauge your interests and put you in groups that are going to best suit your interests. So please fill that out like as soon as humanly possible so that we have as much time to like plan these out. Most likely you'll be in groups of either 2, 3, or 4. We'll try and make as many groups as we can, but we have to be careful with just how many we make because of time constraints. Do you have a question, Kate?
Isn't anywhere except for here, right? Like it's not on my slides on my computer. Like I have to use my.
Well, yeah. So you can scan it, but like we'll upload the QR or we'll upload the slides at the end of the week, like on B courses, like under files, and it'll have the QR code. But like, please do it now if you can. So we keep track of your attendance. No. So they're different. So the attendance form, it was on this slide. This is the attendance. What? Wait, this should not be the oh. This is attendance. Okay. This one too? That's weird. I put that one in there. Maybe Elon swapped it out. Okay, we'll send out a B courses announcement with this survey. So I'll send that out and y'all can redo that. So if that's the same attendance form, then please don't listen to what I just said. We will fix that in an announcement clarifying what I mean. But we will have a form that will ask you about your interests for the final project. So we can put you, if you're interested in like, I don't know, simulations of astrophysics, then we'll put you there. Or if you want to do like a quantum project or something, we can put you in a group with quantum people. Yeah, I mean, like, don't just copy and paste from another assignment that you've done. But yeah, but if you have like an interesting problem, for example, we had a student do a final project on like a double pendulum when she was taking 105, and that was really cool. And it was like simulating double pendulum. So there'll be more on this. We'll start talking about them more in depth next week when we start like worrying about like proposals and stuff. We're gonna have like final project proposals that you'll have to write with your group, and then you'll do your project over the span of the 3 weeks or so. But this is literally just a gauge, so don't worry about starting final projects anywhere yet. It's a ways away. It's just for gauging interest. But cool. So, is there any question? Yeah. Cool. All right. So now today we're going to talk about a recap before we get into today's material. So we have a bit of a longer recap because I want to make sure that we remember what we talked about last week and see how it's applicable to a problem. So first, we have to talk about what a curve fit and what np.polyfit is. So can somebody tell me what the difference is between curve fit and np.polyfit? I'll wait a second or a few. Yeah. 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 So yeah, curve fit is for like any general function that you can code up yourself. It could be sines and cosines. It could be exponentials. It could be whatever you want it to be. But polyfit is only applicable for polynomials. The reason why we have our own function for polyfit is because a polynomial is a very common fitting, like quadratics, cubics, linear functions. Those are very, very common things that we fit. So they just like wrote a polyfit function that we can use really quick and easy. But if you want to do something that's more complicated or more generalized, then you need the curve fit for like the full thing. So that's good. And then what is the curve fit, or I guess what thing is the curve fit function minimizing to determine the best fit to the data? So if I have a bunch of data points, right, and I want to create a curve that best fits that line, what is the quantity that I'm trying to minimize? Yeah, really close, really close. So the residuals are factored into this value, but we call it the chi-squared value. So written as like a chi, it looks like a funky x squared. And that is essentially the residuals summed up together. And you're trying to minimize all the residuals to make the best curve fit line. There's a couple of caveats to how that works with like Gaussianity and whatever, but you can worry about that in a stats course. We don't care about that much. So good. Now I have this problem. Don't worry about reading it so much. I just kind of copied and pasted it. Really, I want you to look at that equation. So this equation is typically you can derive it in like 5A, 7A, your mechanics classes maybe in 105, and essentially is a three-body problem equation. So the three bodies that that are in question is the sun, the earth, and the moon. And we're trying to find the stable points, like the equilibrium points in that system. So you have three bodies. The sun is much more massive than the earth, and the earth is much more massive than the moon. But all three of them are also playing a part. And they, like, when you write down all the equations and you do all the forces and whatnot, the vectors, you get this equation where G is like a constant, and big M is like the mass of the sun, I think, and little m, or no, and big M is the mass of the earth, and little m is the mass of the moon. And I think like big R is like the radius of the earth or something. And like omega is just another like constant that we know. I think it's like how fast they're orbiting around each other or whatever. That's great and all, but really all I care about is that there's this equation, and there's this equation for little r, and we want to solve for little r. And what little r actually represents is a Lagrange point. So you may have heard what a Lagrange point is. This is like a nice diagram. So that equation that I showed you before has 5 roots to it. We call those the 5 Lagrange points. You may have heard about these if you're really interested in like NASA stuff, specifically like putting satellites in space and whatnot. So each of these L1, L2, L3, L4, L5 are solutions to that equation I just showed you. And what they represent is stable points. So you can actually put a satellite on any one of these points and it'll just stay there, like stably. Like it's like a stable equilibrium. So we're actually, I believe it's James Webb telescope is like a giant multi-billion-dollar telescope that we've been trying to build for like what, 10 years or something crazy like that, maybe even more. And what our plan is to have it go all the way out to like L2, I think, and stay there in L2. And that's like many millions of miles away from Earth, like very, very far away, behind the moon, behind the Earth, like way far away from the sun, so that there's no like radiation or like infrared radiation or heat from the Earth distorting signals. It's gonna go way out there, and it's gonna basically slow down and stop right at that L2 point, and it's gonna stay orbiting around the whole system in a stable equilibrium for a while, and that'll allow it to not use any fuel and like observe stuff. So that is like a really practical application of these like just solve. We could like solve this like one equation that I wrote down. So we can solve this like one equation that I wrote down for R And if we solve for like all the different values of R that satisfy that equation, we actually get the Lagrange points. And those can be really useful if you want to like put satellites in space and stuff. So this is like a really practical application. Again, this is just derived from like 5A principles. I'm not going to do physics for you because that's not my job. That's your other class's job. Hopefully they do a decent job. Maybe not though. And my question to you is what kind of Python tools / libraries / functions would you use or what I need to solve this equation for R? So we talked about this last week. I'm going to give everybody about 5 minutes to like reflect on like how they would go about solving for R with this with this equation. How would you like, what would you use? What would you do? What would your steps be with thought process? So we'll take about 5 minutes to think about this and reconvene in 5. Okay. So ask the people at your table. If your table's empty, then turn around and go to the table next to you. Try to stay like groups of 4, I'd say. So yeah, about 5 minutes. Yeah. Oh, sorry, that was. Also, does anybody in the chat have any questions? Okay. All right, I think that's been just about 5 minutes or so. All right, everybody's got like 1 minute, so just kind of wrap up your final thoughts and be prepared to answer questions about it. All right. All right, everybody. So let's reconvene. Hopefully that was really helpful and you were able to think about it. Would anybody like to tell me what their thought process was or like how they would go about solving this question? How do I solve for R? Yeah. Mhm.
I don't know if you have to isolate the R's first so that they're all equal functions, or if you're allowed to just drop fit in the R's on both sides.
Mhm.
But if you need to isolate them, isolate them. And then put S in a few places and find all your points.
Yeah.
Well, I was saying 130 feet from the sun and one in the Kuiper belt, and that'll collapse into your outer and inner bounds. And drop a few guesses in the bounds, and you'll find yourself with many more consequences if you want / there are.
Yeah. Yeah. That was almost a perfect explanation. Thank you. Yeah. So just to reiterate for the people that are on Zoom, as well as if you couldn't hear in the back, what we do is we want to get a function of R. So you want to be able to like have a function that you can write up in Python that's only dependent on R. Everything else here is a constant except for little r. So you just put everything to the left-hand side or the right-hand side, whatever suits your fancy. And then you just like set it equal to 0, like on paper, but then you want to code that up. So everything that's on the right-hand side that's not equal to 0, or I mean, it is equal to 0, but is not 0. You write that up. So it would be like gm over r squared minus gm over r minus little r squared minus omega squared r. That's your function. And it's only dependent on a single variable, r. And then you can use something like fsolve or root from the SciPy library. You can plug that function in, give a couple guesses as to what your r values might be, and boom, it'll slap out all the values that you want for the roots of that equation because we're setting it equal to 0. Similarly, if you wanted to find when it's like equal to 10 or something for whatever reason, then you can like minus a 10 over and then it would do the same effect, just shift it up. But yeah, so that's how we go about doing this question. So this is just like a real practical application of like, yeah, okay, I want to find the Lagrange points in space for our Earth, Moon, Sun system. Well, now you know how, like, this is how literally like scientists would do it. They would use like root solver finders that are already coded up in like the SciPy library. It's a very, very common library. It's used everywhere in science. And they would do that really quickly, nice and easy. It's not some crazy abstract concept, I mean, to be able to do unless you wanted to figure out how to code it up from scratch. But yeah, this is how we would do it. So that's cool. You have a question?
Are 3, 4, and 5 at an equal orbit? And if so, how are they defined in a formula that doesn't have a theta component?
I see what you're saying. I believe, yeah. Well, what we're assuming in this problem is that Earth and the moon have circular orbits around their respective counterparts. So moon is circular around Earth and Earth circular around the sun. So that simplifies the equations down drastically. Technically, there would be like a theta component in an ellipse equation, but since this is only a circular equation, there isn't. It's all just r. It all goes around like in a circumference, yeah, whatever the word is, circumferential, right? The word, yes, the words are difficult. But yes, so there's no theta component in this case. Does that answer your question?
Yeah, so they're created by eliminates our ability.
Yeah. Now, if you want to like actually do the real thing, then it's actually a really more nasty function. It's not as pretty as what we have here. There's like sines and cosines of thetas and phi's and whatever, but or at least for the simplified problem, this makes our lives a lot easier. Cool. So, all right, let's get into differentiation. I have so much on this slide, so I'm going to hide my stuff. Hide meeting controls. Cool, and we'll stop it right there. Cool. So we're going to talk about differentiation and integration today. That's our topic. So we'll start with differentiation. I'll try to keep this short and sweet so that it's not overbearingly like overcomplicated. So again, we use packages. This is like the beauty of being a scientist, not a computer scientist. We actually use packages. We don't code them from scratch. So we're going to use other people's packages. There's a derivative function in the SciPy library dot misc, scipy dot misc. We do from scipy dot misc import derivative, and that gives us a function that calculates the derivative. Really nice, super easy. The arguments to that function, func, is a function that you have to define yourself. And it's typically a like one argument function, so like f of x or f of y, but typically it gets a little bit more complicated when you want to do like f of x comma y, like a function that's multivariable. You have to be a little bit more careful on how you define that. So yeah, it's like it's a 1D function, takes in like one single variable. In this case, it's called x or x naught. And func is the function we want to, this should say differentiate, not integrate. That's a typo. But x naught is the point where you want to evaluate that derivative. If you want to do it over many different x's, then it's going to be like an array of values. Dx is the spacing. So like how fine of a like differential step do you want to take for calculating it? And then n is the order of differentiation. So n equals 1 is like the first derivative, n equals 2 is the second derivative, and all the way on to like how many derivatives you want. You'll investigate this a lot more in your homework that is going to be released today, that you'll be working on for the rest of the week. And just to remind you of like how a derivative is calculated, like numerically, not just analytically with like chain rules and stuff, but like how does a computer do it? Right? It's just defined as like the limit of like f of like a center point plus h, or f of c plus h minus f of c over h, where h goes to like really, really tiny, goes to 0. So essentially we take like a differential x step and a differential y step, and we calculate the slope between. We're looking at the instantaneous change of that function. This is all just recap from like Calc 1A, or maybe if you took like calculus in high school, like Calc AB. Yeah, so is there any questions about like numerical derivatives? Just like, it's just this equation, basically delta y over delta x, the tiny, tiny differential slope as we get tiny and tiny. The dx changes how small of a slope we make it, or how small of steps we make that slope from. Any questions? Your question?
This is producing not a function that is the derivative, but the number that the derivative is.
Yes, yeah, it returns the value of the derivative of that function at a point. So if we wanted to essentially do it over like a or like, I guess here's like an example of how we would use it, like just a tactile example. You could define a function, func of x, which is just x squared plus x, and you can plug that in instead. This is like one example with a lambda instead, but the normal way would just be to plug in that function, literally the same syntax here, like you just plug in func, or you can do it with a lambda function. We talked about this a little bit a while back. I think Emily talked about this in her lecture. It's very, it's just kind of like a shorthand notation. It's kind of meant for situations like this where you don't want to really like take the time to make like a whole big function with like a def statement and everything. You just want it really quick and dirty. You don't even want to give it a name. So you could do like a lambda statement where x before the colon means the variable x that you're going to take into your function, and then we return x squared plus x. Very quick and dirty version of it. It's the same thing. It's literally the exact same as this func of x version that we had on the previous slide right here. It's just more than 2 ways to do the same thing. And then we're evaluating it at x is equal to 17. And that's just, it gives you the derivative at that point. Yeah.
Do you know if the GS parameter is optional, and if it is, like, you know what it defaults to? Because I assume if you like decrease it to something, like, is there the risk of either rounding errors or like?
Yeah, that's a good question. I can't remember if dx is an optional parameter. It is? Okay. There's your answer. I guess the default is for dx. Oh, okay. Yeah, so for the people on Zoom, the default dx value is 1.0. Obviously, that's a pretty big number if you're dealing with like small range of function or like small ranges or domains. So make sure that you're like explicitly stating what your dx is, or else it'll like severely not, or be like a severely bad approximation. So I recommend keeping your dx around 10 to the negative 6, but I always encourage you when you do derivatives to play around with like how fine you make it, because you might get into like numerical errors and noise. So if you make dx like 10 to the negative 100, it's going to like kill your computer because it has to take 10 to the 100 steps to finish at least, right? So definitely don't do that. But 10 to the negative 6, 10 to the negative 5, maybe even 10 to the negative 4 is pretty small enough that it can do a really good approximation. But try not to go too low or too high. Like 10 to the negative 6 is typically a good starting point, and you can play around. And if you change it and your answer changes, that's a bad sign. You definitely don't want to see your answer changing depending on your dx size. So, just play, like, that's something that you'll have to play around with. If you ever take a derivative and you want to trust the value, play around with different dx's to make sure that it's trustable. Is there any questions about like derivatives before we move on to integration? Cool. All right, let's move on to numerical integration. This is also just as useful in other ways, or in some ways, I would say it's even more useful. Integrals are like super important for like anything. So typically in high school, you may have learned, or in college, you may have learned that Riemann sums are a good way to approximate an integral. There's like the centered left and the right Riemann sums, where you're like literally just making rectangles underneath the curve that looks like this. Hopefully this will work. Right, where you have some function and you draw a bunch of little rectangles, and you can like specify their dx size, and then the height is just the function at that point. And you can be like specific where you evaluate. So you can like evaluate on the left side of the rectangle, or the right side, or the center, or you can actually make like trapezoids that are even better approximations. You can do all these things, all these different ways to approximate an integral, and that's great. That's like what they taught you in high school, but we don't use those because they suck. So there's other rules. There's like the Simpsons rule. I was taught this in 77. It's really just this equation. I don't even really know why we would ever use this one either, but just know that it's there. It's just like another like dot simps instead of like dot traps, for example. But it's a good way to check to make sure that your like values are consistent with different methods, right? They should all kind of give you roughly the same answers. But you'll see, we'll do an example where you can see that they actually do change a little bit depending on like how fine of a resolution you put it in, and like what kind of functions you're using and whatnot. Oh boy, internet's unstable. I'm going to, okay, I'm going to keep this up here just in case. Hopefully it doesn't cut out. So yeah, anyway, there's that, or like there's Simpsons rule, but I got to tell you about Gaussian quadrature. You probably have never heard of this unless you're like some really like advanced math student or something. But Gaussian quadrature is probably the like best integral technique ever. It's super useful, and it like completely blows all the other techniques out of the water in my like from my experience. So I made this meme from The Office. I hope you like it. Yeah, I'm not going to read it because that would kill it, but like, yeah, I think it's true. And like, what is it? That's a good question. Essentially, like in a Riemann sum, we're allowed to, where we have to keep like finite dx, and we keep dx constant when we make our rectangles. Gaussian quadrature is like, nah, we can use whatever size we want, and it like makes it a lot more robust, and you use less points to do it. So it's like, not only that, it's like faster, it's more accurate, and it just makes more sense. And you're using like curves, not just like straight lines. So it's even better, especially for like smooth continuous functions. So yeah, I think that's that. I want to do a little demo with like while loop integration, just to like go back all the way to our roots of what a while loop is and kind of use that to integrate. We can do a really crude approximation for integral. So again, this is just like the picture I was drawing on the board, but this is essentially what we're going to be doing today, or like doing for a small demo. I didn't like send out like a notebook for you to download because you can kind of just code this up really quickly in like 5 lines. So we're just going to do that. This is the equation we're going to use. You may have seen this. Like, you can represent an integral as the limit as n goes to infinity of like a bunch of like f of x times dx, or delta x, where delta x is like the width of your little rectangle. And we can like specify dx by like the bounds, like subtract the difference between the bounds divided by the number of steps we want to take, and we can evaluate these different values. So if we just go ahead and make a notebook, Ooh. I'll just make a new one like this. You feel free to follow along with me if you would like. You don't have to if you don't want to, but I figure it might be kind of fun. Let me get nice and zoomed in. Can everybody see that? Yeah? All right, cool. So we're just gonna make a function. We're gonna call it while int, I think. Or we're just like using a while loop to do an integral, and it's gonna take in several different arguments. So I'm gonna call g like the function that we want to integrate. I'm gonna say a is like the first bound, b is the second bound, and maybe like we could say like dx is gonna be the like the fourth argument, where it's just like how fine of a rectangle do we want to make. And then we could just start by saying, like we start by like defining a variable inside of it, a local variable. We're going to set it equal to a. And then we're going to also define like an area variable. And we're basically going to add to the area each time we go through a while loop statement. So we're going to say while x is less than b. All we have to do is say like what our y value, our height of that rectangle that we're going to draw is just going to be g of x. G is the name of a function, any function. We're setting g to be like a variable inside this function that can take an actual function that we write elsewhere. And then all we're going to do is just say area is equal to area plus y times dx. This is literally just copying that equation that we wrote down, f of x sub I times delta x. And we're just adding it every time. So area is equal to area plus that. And then we're also going to do the same thing with, we're also going to do a similar idea where we're going to add a dx to x every time, right? Because we're already evaluating that little rectangle. So we need to move on to the next rectangle every time in our while loop. And just to remember, like the structure of a while loop, we have while, some condition. We have the body of our while loop, like what it's doing something that we want it to do. And then we have a change to the conditions that's going to make sure that we don't have an infinite loop, right? So if we didn't have this x is equal to x plus dx, we would just have an infinite loop because x would never change. It would just stay at a, and it would always be less than b, and we would make our computer sad. So we don't want to do that. And then at the end of our function, we want to return the area, right? So now we can evaluate our function, or like we can take the integral of something. So let's just go ahead and print the value. We can just like make any function. We can even use like a lambda function if we want to be fancy with it. So I'm just going to say like some function that just does like empty dot cosine of x. That'll be our function. And we will, am I doing this right? No. Parentheses. Yes, here's the parentheses. There we go. That's going to be like our function that we put in. Our g is literally like this lambda function that takes in an x and spits out the cosine of x. And we can set the bounds. We can make them like 0 and like pi over 2. np dot pi over 2 is just pi over 2. And then we'll set dx equal to 1e negative 4 to start with. And if we run that, it doesn't work because numpy is not defined. That's fine. And if we run that, there. So it's not perfect. You can see there's like, it's very crude. It would get better if we make the step size even smaller. So we can make it like 10 to the negative 6, for example. And this will take a while because it's a lot of things to add up. But you see it gets even closer to 1. And if we make this 10 to the negative 9 and the negative 10, it'll get even better because we're making more and more little tiny rectangles. Just basic calculus. This is what we learn in like 1A or like 5A, or not 5A, like AB from like Calc AB in high school and stuff like that. Is there any questions about what I did here? Did I go too fast or was that good pace? Cool. All right, so let's go back to the slides. So that was like a little demo of like how to do while loops. Nothing too crazy. It's literally just coding up this equation and doing a while loop to add it all up, to add up the area, and that's great. So now I just want to talk a little bit about numerical integration further. So I have so much stuff. It's like numerical integration is extremely important in physics as well as astronomy and really all natural sciences, to be honest. We're going to talk about differential equations later in the next week or so, and that will be like integration and differentiation is a crucial part of that, right? If you want to do projectile motion, F is equal to ma, you take a derivative of that or an integral of that, and it gives you the next like projectile motion equation all the way down to like the familiar projectile motion equations you might have learned in like high school physics. So they're super important. Differential equations that kind of run the world, and being able to do integrals and differentiate with a computer is like allows you to open up your doors to all these problems that you couldn't just do with pencil and paper. So it's important that we have this skill. So now this time for integration, we're gonna just import our nice little functions. So we're gonna import scipy.integrate. As integrate, it's just like the integrate part of the library. And then from that, or like another way to do it, you could just like integrate, or you can import like a specific function. So we can import like a quadrature function, or like we can import a trapezoid function, or like a right Riemann sum or something stupid like that. And yeah, so there's lots of different functions at our disposal. In fact, here's like literally all the different functions that they have to allow you to take an integral. Like, I don't know why there's so many. Like really, like it seems kind of redundant, but the stars are next to the ones that I find the most important. So quadrature is at the very top. That's like the golden standard. It's amazing. It's always right. It gives you like the best results, in my opinion. And then DBL quad and TPL quad, those are the same thing, but for double and triple integrals. Nice. And then like the trapezoid function and the Simpson function down there at the bottom are the other two rules I was talking about with doing like trapezoids and like Simpson's rule, which is just some approximation equation. So there's tons of different options at your disposal right here. And we're just going to explore a couple of them today with like a demo and the rest of the lecture. So single variable integration, we all seen this, an integral from a to b of f of x dx. Again, we import a function, scipy.integrate, import quad, very nice. We use it. You just like call the quad function. Func is just the function you want to integrate. Same style as we had with the derivative function. You just have to write your func function beforehand. It could also be a lambda function if you want to do it quick and dirty. A is the lower bound, B is the upper bound. You don't even need to specify with quadrature. You don't even really need to specify a dx because it makes its own dx's based off of what the most what the most efficient way of doing it is. So you don't even have to worry about that. You literally just give it a bounds and the function. And what it'll spit out is it actually spits out two things. And we'll see this in a practical example. The first thing is going to be the actual value of the integral over those bounds. And then the second thing is going to be the error on that because it's just built different. It's really cool. It just like makes your life so much easier, like knowing that knowing how bad your integral was. It gives you the error. And usually it's like some ungodly small number, like 10 to the negative 15 or something. So you could assume it's basically right. And we'll get to an example of how to use this. I'll do a little bit more with the demo. Double integral, not much different. You just import double quad, DBL quad. So yeah, you give it a function of y and x or x and y. The lower bound of x, lower bound of y are a and b, and then like g function and h function are like the bounds for y of x. So if you remember from our like math 53 days, or if you haven't taken it, that's fine. You'll learn about it soon. You can basically have an x1, y1, x2, y2 as your bounds, and actually like y or like the x1 and x2 can actually be functions of y, or similarly, or no, y can be functions of x for their bounds, and you can evaluate from different values. So like, I don't know, I guess I could draw something really quick. I don't know. Yeah, it's fine. I'm not going to draw 3D values, but essentially your y bounds can be functions of x, and you can evaluate. Yeah, I can do it. Like this, where you have like specific bounds in the x direction and specific bounds in the y direction that are dependent of, like this is a bound of y of x. You can integrate from like one bound to the other bound as a function. So you can specify g function and h function as different bounds, or you can just make them constants too. But that's important to know if you want to do a double integral, and it'll spit out the value and the error. That's what integral is, same as like the single quadrature integration. And then similarly, we can also, or this is like an example of how we use it. So here's like an integral we want to use, or we want to take the integral of. We want to do integral of x, y, dy, dx from 1 to x squared and 3 to x, or 3 to 6. Your function is just going to be x times y. We define it there. We use func, or we plug it in. Our a and b bounds are 3 and 6 for like the x, or for the x values. And then the y bounds are going to be from 1 to x squared. And notice how these have to be functions. If I just wanted to spit out a constant value, then I just say that like no matter what I take in my x value, I'm always going to return a 1. And then if you want it to be dependent on x, then you just do no matter what my x value is, I want it to be x squared using these lambda syntax. If you don't remember the lambda syntax, please ask a question about it, or like, I guess I should ask, does anybody not remember the lambda syntax? Yeah, so the lambda syntax, just for reiterating like how it works. Lambda is a keyword that Python already knows. It basically indicates that everything after, or whatever comes after this, is going to follow a function syntax that's specific to the lambda word. So anything that comes before a colon is a variable. So it takes it, when you say lambda space x, it's saying that x before the colon is the variable x in your function, the same way that you have an x here. Like it's just an argument. And then whatever's on the right side of the colon is going to be the return value. So in this case, no matter what my x is, I'm going to return a value 1. With this function, I take in a variable x, or an argument x, and it'd be the same thing as if I said return x squared. Instead of return x times y, it'd be like return x squared, and there's no y here for like this lambda function. Does that help or no? Yeah. Yeah, it's like quick and dirty. If you don't care about like the name, like you don't want to keep the function later, you just want to integrate that value, you can just do it quick and dirty like in one line. So you don't have to like do multiple defined statements. It's like literally you never even have to use this if you don't want to. It's just an example of using lambda functions. They're just all like shortcuts basically, because people were so used to writing like little tiny functions like f of x squared, or like f of x is equal to x squared, and they were tired of having to write out like a whole defined statement and like do like a tab or like an enter press button. So they like found a quick way to do it with lambda functions. It's like a quick thing, but it's a very shortcut method to doing that. You can do the same thing with a defined statement, regular function. Cool. Yeah, and similarly, you can do a triple integral with TPL quad, and it'll do the same thing just with a triple integral instead of a double integral, which you may need to use for like E&M or something, whatever that may be. So I think I have 5 minutes of demos planned, so let's go ahead and get to that. Just putting all this into practice. So let's go back to the derivatives, and we'll just use it starting from scratch. So let's import what we need. We're going to import scipy.misc, we're going to import a specific function from there. From the scipy.misc library, we're going to import the derivative function. And I'm also going to import matplotlib because we want to plot stuff. Let's put this up there, this over here. And then let's define a function. We'll call it f of x. And all it's going to do is return the sign of x. So np.sign of x. Cool. That's just a generic function. And then we're just going to evaluate y at 0, like the derivative of y at 0. So we're going to use our derivative function, derivative. Yep, I spelled that right. And we're gonna we put the name of our function. So I named my function f of x. So I'm going to put the name only, not the argument, but just the name. If I want to evaluate it at one point. Cool. And I'm going to evaluate it at 0. And we'll set dx equal to, I don't know, 1e negative 6, like how we had in lecture. And we'll take only the first derivative. Okay. And if we print, oh my gosh, I cannot type, like dy dx at x equals 0. If we just print y at 0, we'll see that it's like 0.9999934, which the derivative at 0 of sine of x, right? It should be like just about 1, I think. Yeah, right? Yeah. Cosine of 0 is 1. Yeah, okay. Cool. So that's as we expect. That's a good thing. And now now you might be asking, okay, I want to plot like the derivative as a function of x. Like I don't want to just take it at one value. So how do I do that? So this is how you would do it. You say x is equal to np.linspace. And we could just do some bounds. So we'll set it from like negative pi to pi. And we'll do like, I don't know, we'll set 1,000 little steps in between, 1,000 evenly spaced steps. I think that's a fair enough number. And then we can calculate the derivative. So like y derivative is going to be like an array of values that we're going to use x to calculate. And we're just going to use the derivative function. We're going to plug in our function f of x, which we said was sine. We're putting the name. And then instead of a 0, we're going to actually just put the whole x array. So notice it might even be better to say like x ln or something like ln, like the entire like x values from negative pi to pi, all 1,000 of them, that array. And again, we'll set dx equal to 1e negative 6, which is the same thing as saying 10 to the negative 6. And then n is equal to 1. And if I wanted to, I could do a little plot. Or let's set our figure. Oh my goodness. Size is equal to like 10,6, not 76. That would suck. And then plot. We can first plot like x comma f of x, and we'll make it red with a straight line or with like a solid line, and we'll give it a label so that we know what we're talking about. We'll call it f of x. And then we'll also do a similar thing, but we'll just plot the derivative. So oh, I almost forgot. I called these x ln. So these take in the ln space. Cool. And we'll make this blue. And I'm almost done. This will just be f prime. Yeah. F prime of x, like that. And then plt.legend, plt.plot, or dot show. If we do that, now we see the red curve is the sine curve and the blue curve is cosine. And we plot the derivative and like derivative or y prime of x or f prime of x versus x, and then f of x versus x, which is great. And I realize it's 3 o'clock, so I won't hold you any longer. Your homework will investigate like the different rules. You're going to use like, I don't know, it'll be like integrate dots, or it'll be like, you'll use like the traps function from SciPy. You'll use like the simps function and the quad function. Those will be like things that you'll investigate on your homework. I won't do anything more, but yeah, just know that that'll be on your homework. So yeah, you have a question? Oh, scroll up. Yeah. I hope that was, I know like derivatives and integrals are not super interesting. I tried to think of ways to make it interesting and I just couldn't, like sines and cosines, but the next lecture will be more interesting because we'll actually apply it to physics stuff and it'll be a lot cooler. But just know that you have this at your disposal. You can take derivatives and you can take integrals in Python, and you're going to do some of that on your homework. All right, cool. So that's everything for lecture. I'll see you all on Thursday.